the fantasy of every ring want to be a polynomial ring. But if you go to other groups, then all these rings are Cohen-Macaulay.
But and then you didn't say, but I guess
okay,
you mean
then
that the complex is Cohen-Macaulay if and only if
a complex is Cohen-Macaulay by definition if it's ring, if the face ring is Cohen-Macaulay. And it turns out that being Cohen-Macaulay is an interesting property.
What? By definition, it's so easy to say.
No, not by definition. You can have two definitions.
Cohen-Macaulay if and only if its face ring is Cohen-Macaulay.
Yeah, you can have two definitions of Cohen-Macaulay. One, it's Cohen-Macaulay if and only if its face ring is Cohen-Macaulay. The other, it's Cohen-Macaulay if it satisfies this condition of the homology. And they are equivalent, but this is not an easy theorem. This is a...
And it's always over a ring. Like
yeah, it's always over some ring of coefficients.
Yeah, it can be, and the equivalence is over every ring.
Yeah, the equivalence of every I don't know, commutative ring.
Yeah.
Usually, when I think about rings, I think about field or Z.
Okay.
Because Z is also important. So unless you can promote Z to be a field, then I want to think about Z and the field. Anyway, so this is the definition of Cohen-Macaulay, and it is. You see, it's.
But if you know something, if you really know that a complex is Cohen-Macaulay over some ring,
yeah.
What do you get out of it? Some new information, what except of this?
No, you get a lot of information from it.
Like what?
So there are a lot of things a lot of interesting combinatorics that come from this fact that it's Cohen-Macaulay. I can give some examples, but I may return to it. But being Cohen-Macaulay has a lot of combinatorial consequences. Another example is you can look at super solvable groups and the rings of subgroup, the lattice of subgroups, and this is a super solvable lattice, and this is also Cohen-Macaulay. So this is it comes in also surprising places. And, okay, in any case, this is it. And I will tell you the connection. Okay, so there is one. Okay, so I tell you one of the combinatorial connection is that one thing you can do when you have a shellable complex. You see, shellable complex. You have shelling of type A. You see, of type. So what is shellable? Shellable complex. You start to shell it. You have shellable steps of type I and D. So you delete a maximal face which is of size D, or dimension D-1, and a free face of dimension I. And you can count how many shelling steps are there of type ID. And you can denote this number by HI of the complex, which depends on the shelling. Now, there is an easy combinatorial fact that these numbers do not depend on the shelling. So they actually just depend on the combinatorial of the complex. Now, okay. And now you can look at this description. And now, if you are walking over a field with infinite field, over when the field of coefficients is infinite, but let's say it's R or C, then you can take these thetas to be of degree 1. So when we think about the symmetric function, we didn't take them over the elementary symmetric are not of degree 1, but you can always change and take them to be degree 1. When you take them to degree 1, then you also have these etas. These etas, there will be various etas of different dimensions. But the number of etas of degree k does not depend, even if you have different representation, it will always be the same. Not only the number of etas of degree k will be the same, it will be precisely this hi. So this is the basic connection between the ring theory and the combinatorics. If you have a shellable complex, then this hi count the number of etas of degree I. But if you have a general Cohen-Macaulay complex, you don't have a shelling, but you still have these numbers. So sometimes the ring theoretical concept allows you to extend the combinatorial object to a situation where it doesn't exist, but it still have some algebraic traces. Okay, so this is an example where this is. Now, of course, once you know that this hi of k is the number of etas, then immediately this gives you an equality that this is at most. The number of such etas, it can be at most the number of monomials of degree k in a ring with n minus d variable, because you already killed d variable. So this is n minus d plus k minus 1 choose k. So another consequence you get is this consequence. So this is also a famous theorem. It's called the upper bound theorem for Macaulay complex F. This was proved by Stanley in 1975. It was a big deal. So maybe we'll take a break. So we'll take a break and then we will continue.